So our second speaker in this session is Peter Chalner from National Oceanography Centre at Southampton. We're talking about design for smoothing parameters.
Okay. Thank you very much. I feel a little bit of a fraud here, actually, because I'm not really a design person, or I wasn't really a design person before this program started. I'm interested in predicting climate and in the uncertainty you get when you predict climate. So I want to answer questions like this. What is the chance that the global mean temperature will be greater than 3 degrees higher than present by 2100? Or what is the probability that the overturning circulation in the North Atlantic will collapse by 2150? So these are very important policy relevant questions that people are asking. And the only really where we can get at those questions is through models. We have no data about what's going to happen at 2100 or 2150. So we have to use climate models. This is an example of a climate model. In fact, that's a comparison with data, but it doesn't really matter. It's the only picture I could find. They're very high. This one is very high resolution. It takes, the time step is quite small. They take a lot of computer power. So using the biggest computers in the world, this will take weeks to produce. Well, that one, in fact, I think they've never actually done a 100-year run, but they take forward 100, 200 years. They take a long, long time to run. And that means that we need really good designs of our experiments because we can't afford to waste runs. They really can't do that. That's how I got into design. And partly through the fact that the people who normally do these things do appallingly bad designs. Things like one at a time changes with the one in the middle and things like that. So let's look at how we actually would analyze a computer experiment. We'd run a designed experiment to span the input space, the parameter space, using something like the designs that Henry or Hugo were talking about. We then build what's called an emulator for our computer model. And I'll explain what emulators are in a minute. And then we'd use this emulator to do our inference. So building this emulator is the really important part because it's the emulator we do the inference on, and then we sort of feed that back to tell us what the computer model would do, plus some uncertainty because we've built this emulator. So the emulator, well, we generally use Gaussian processes to build emulators. And if anyone doesn't know, it's a Gaussian process, stochastic process, where all the marginal and conditional distributions are normal. And you can think of it as an infinite dimensional version of a normal distribution. So our emulator, generalizing slightly more from the Gaussian process, this is our computer model, or our emulator, and we have two parts to it. We have a deterministic part, a regression part, which is the linear combination of some basis functions. Henry talked about Fourier functions. A lot of people use polynomials. It doesn't really matter. It's just something that takes out the sort of gross features of the computer model. And then we have a zero-mean Gaussian process that sits on the end. And that takes out the local variation within this large-scale regression-type model, so we can fit the little bumps and things. And where we get the great gain from is this is correlated. So this is a smooth function. So having a point here tells us something of what's going on here. So putting that additional assumption in, we can actually get a spread out our data. And this is defined in terms of some variance and some correlation function that tells us how a point here relates to a point somewhere close to it. What I'm going to talk about is, can we actually design to get these parameters rather than these large-scale regression type parameters. So we need to estimate these betas, the sigmas, and these correlation function parameters. There are pretty well established Bayesian methods for getting the betas and the sigmas. If you look at the Oakley and O'Hagan paper, for example. those Bayesian methods don't get us to these correlation parameters. The full Bayesian solution is just too hard at the moment. So we use maximum likelihood, or sometimes cross-validation, some other method to get these correlation parameters. And basically that's a smoothness parameter, and here's an example of what one of these correlation functions might look like. This is a squared, exponential squared correlation function. This one's quite a favorite. We use this one because it's nice and smooth. It has all derivatives, and it exists in however many dimensions you have. You could take this to be a linear, and then you don't get this property of having the derivatives, which means you get a rather rougher function. So this is the one most people in practice would use, and we have to estimate this b here, and that's quite difficult. Doing this practically, the hardest part is estimating that b. We have nice regression diagnostics to estimate the regression part. We don't have nice correlation diagnostics to get the correlation part at the moment. So this is quite hard to estimate. Here's an example of what an emulator looks like. I've got some computer model, and I run it in some limited number of places. I then take away the computer model because I don't actually know anything other than where I ran it, and I can now fit an emulator to that. Now, there's a few things you should note here. Is that the emulator is a perfect interpolator of our data, because we're emulating what the model would tell us, and we know the model results without any error. This is exactly what the model gives us. We will ignore numerical error and the fact that computers don't all give the same answer. But, so it's a perfect interpolator, and these uncertainty bounds go down to 0 here because we have no uncertainty. We know exactly what's happening there. So you get these sort of butterfly shaped things that sort of compress down. And then if we put my computer model back on top of there, we can see it does a pretty good job. I'm always surprised by how well it does, given I only give out 4 points. But now, I've not talked about what the space scale was I put on there, what these smoothing parameters I put on there, and I've chosen quite a good one for that example. So let's just see what happens if we change this smoothing parameter. So we can go from a fairly smooth function here through to a not so smooth function here to one where the space scale has got very short, the smoothing scale has got very short. So what's happening here isn't related much to what's happening there. And you can see what's happening with the uncertainty bounds is they're just ballooning out to the uncertainty that comes purely from the regression part. And this blue line is that regression part in this model. And you can see that my emulator just folds back to the regression part, and this flips up to the points when it gets close. So this local effect has become very local. This is not a good emulator. This one here is really nice. And so estimating these smoothness parameters is important. Now, if I'd put more effort into getting this regression part right, and I'd caught some of this, put a quadratic or a cubic through here, it wouldn't be so important that I'd got the regression, that I'd got the smoothing scales wrong. So there's a trade-off between getting these correlation scales and building a good regression part to the emulator. I'm very lazy and tend not to spend a lot of time on this. Some people, Michael Goldstein at Durham, John T. Ruggie at Bristol, will spend an awful lot of time trying to get this regression part correct, and therefore the smoothness scales don't matter so much. Okay, so the current designs are based on space filling, and we've had a really good talk about space filling designs before this. Most people at the moment would just use straight Latin hypercubes, maximum Latin hypercubes, pushing the points apart as far as possible. Sobel sequences are becoming more used. But these tend to push the points as far away as possible to fill space the most economically. Now, if I'm interested in estimating these smoothness parameters, which are all about the local behavior of the function, is it appropriate to have a design that just pushes everything as far apart as possible? And can I do better? Now, intuitively, you probably don't want the points pushed as far away as possible. And in one dimension, you might think, well, I'd like something more like a harmonic series to capture the shape of this correlation function. I don't want anything too close together because that has correlation 1 and that doesn't tell me anything. And I don't want anything too far apart because that has correlation 0 and that doesn't tell me anything. But there's a part in the middle here where I'd like to sort of get all space scales represented so I can actually tie that function down. Now, a lot of people have talked about that, and at the last DEMA conference, Daniel Hagen gave a talk about computer experiments where he said something very similar. We need designs that do that. I'm now going to try and put forward some designs that attempt to do that, and we'll see how well we do. Paper in 2004, Zhu and Stein look at a related problem. They look at the geostatistical problem, and in geostatistics, you want to get those correlation scales, but you don't have this underlying regression formula you're trying to get. So you don't have this space-filling design already. You just start with a blank sheet of paper and you design. And they show that you can get the Fisher information matrix for the smoothing problems given some design. And then you can set up the optimal design by maximizing this utility. So we have the log of the determinant of the Fisher information matrix times the prior, and we just integrate that over all possible scales. And we look for the maximum of that. So what I'm going to do is take this one step forward from the blank sheet of paper into having a space-filling. What's next? The next picture. Yeah. I'm going to have an initial space-filling design, and then I'm going to add additional points to maximize this utility. I don't just want to estimate the smoothing parameters, so I have this initial space-filling design to get the regression part, and then I'm going to maximize this utility on the next part. And to make life easy for the initial implementation, and the fact that I've done all this work in the last 2 weeks, we're going to work just in 2 dimensions, and that makes it nice to visualize. We're going to force everything to be isotropic. I'm only going to have one space scale, even though I've got 2 dimensions. And I'm going to put a gamma prior on my space scales with a mean of 1 and a variance of 10. So that's a fairly non-informative prior. Now, what I'm expecting to get from this, and before I show you the picture, I'll show you what I expect to get, is you'll have points in my space-filling design, and I would expect to get high utility sort of in halos or roundels around those points, as it says this is the sort of space, the optimum space to put the points apart. So let's see if that's what we actually get. So here I've taken a 5-point Sobol sequence, and I haven't added the farther point, or whatever you want to call it, down in the 0, 0. And I've calculated the that utility for each point on a 100 by 100 grid. So this is the utility of adding an extra point to my design at each point on a 100 by 100 grid, and red is high utility and yellow and white are low utility. Now, I'm not getting nice little roundels around my points, but I think I can convince you that I'm getting something related to roundels around my points. The maximum is along here, and that's linking these 2 points, which are the closest together. So the absolute maximum sitting somewhere around about here. And you can see that yes, it likes sitting between those 2, because there it gets 2 small distances. If you go out here, there are no small distances, so you can see why this has got low utility. Then you get these little sort of bits out here, it's close to there, but it's a long way from here. So the utility is sort of medium high. And similarly, that's why you get this sort of cross structure, because as you go down here, it's closer to those two and not so close to the others. So I think it's the interaction of lots of these different roundels together, but that's a very intuitive post hoc explanation of this diagram. And I mean, at the initial workshop, I presented a diagram a little bit like that, and I couldn't understand it at all. But I think with 5 points, you start to understand it. If we go to 10 points, it gets a lot more complicated. And I think we started at 10, and that was a mistake. So this is now the utility for 10-point Sobel sequence, but I've reversed the color scale just to make things confusing. So this is now my sort of ridge of high utility along here, and I've got another sort of lower ridge here because there's 2 points relatively close together. Why these 2 points, which seem to be about the same distance as these, don't have quite such a high ridge, I'm not sure. It's probably the influence of these. All the points interact to give you this utility, so you can't, I think my intuition of little roundels around the points doesn't work because the space scales are large enough to fill this whole area. My prior doesn't limit me to small space scales. In fact, it pushes them much wider than this 1 by 1, and maybe that was a mistake as well.
Sorry, those white dots.
Those are the original Sobel sequences. For some reason, R has put the little circles in the top corner of the Yes, I wiped out the utility where there's already a point, because there's no point putting another point out. But it's the vagaries of plotting. So let's now see if I start adding points to my sequence, what actually happens. And I'm going to add 5 extra points. So I start off with my 10 points, and here's the utility. So I add a point, and it puts one here. So I add this extra point, and that knocks down the utility along here. But this ridge is still the place it wants to put one, so it puts another one there. And then that knocks this bit down. But it's now raised this part of the ridge up, and it puts one there. And basically, it sort of fills in this ridge of high utility along here. So that's adding points one at a time. Now we might say, well, we might want to add points n at a time. Can we do that? This is also very computationally intensive, calculating this 100 by 100 grid and calculating the maximum that way. So if we want to compute the next n optimal points, just working out the maximum by calculating all possible values becomes impossible. So I've sort of set up a simulated annealing method to find the maximum or the near maximum. You can never really trust simulated to get the absolute maximum, and the sort of simulated annealing I've put together hasn't been particularly tuned yet. So we're getting good designs, but I'm not sure we're going to get optimal designs out of doing maximum. But let's just see what we get. So here I've got the 1 at a time 5 extra points, and you can see here's that ridge along there. And here's my 5 at a time. And we've got some extra points along this ridge, but we've got a couple of points out here. And if I overlay them, it's probably a little bit clearer. So these are where you get a circle and a triangle are the original Sobel points, because they're the same in both designs. Here's that utility ridge we had, and we've now got 3 of my 5 at a time points there instead of the full 5. And I've got 2 points out here. Now we have a problem. I have a problem. Are those 2 points out there because it's a really good place to put points, or is it because my simulated annealing hasn't actually given me the optimum? And I don't have a solution to that problem at the moment. I need to run the simulated annealing from different starting points and to run it for longer and to tune it a bit better. But it's intriguing that it's got points out here. These tend to be in areas of fairly low utility for the 1 at a time extra, but it may be that the common distances between them does something, and I'm not absolutely sure about that yet. I'd welcome comments. Okay, now in a practical application, you'd come to the point that I can afford 5 more extra runs in my computer experiment, should I put those 5 extra runs by adding these 5 smoothness points to get these smoothness parameters better, or would I be better off just carrying on filling in the Sobol sequence to fill out space? And how would I decide that? Well, here's my proposed test, because I haven't actually managed to implement it yet. We have a proposed new set of points, and I will use the emulator I built up for my original set of points to emulate the function, the computer model, at these new set of points. So I now have an estimate of what's at those new set of points, and I'm not going to use the expected value from the emulator. I'm going to sample from the emulator. So I'm going to sample from the emulator at those points, and then I'll rebuild my emulator, assuming that those sample points are true. And that will include re-estimating the space scales, the smoothness, which is what I'm designing for. And then we can use that emulator to estimate some metric over the space. I've said here we could integrate the uncertainty, so we'd take those designs that make the emulator better everywhere. We could do something on predictive power, or there's lots of metrics you could use there. And then we just resample around here, resample around this loop to actually build up some sort of distribution of how well I would expect, because I'm based it purely on the emulator, the extra design to do, and then I can decide which one's better and actually go away and run the computer code. Okay, where next? Well, finish implementing the scheme, tune up the simulated annealing, get the test for which points I should use, and then go to something rather more realistic than 2D isotropic. The computer models we work with have something from 40 to 100 unmissing parameters, so that's 40 to 100 dimensional space. If I included the inputs, they would have millions of degrees of freedom, so we don't do that. But we must step up the number of dimensions. We're way higher than the geostatistical problem. And then to actually try it in some real computer experiments and see, does it actually improve things? And I want to thank Jim Gattaker, who used to work for me, has now gone back to Los Alamos, who did some of the initial work on this, and I had some very useful conversations with Dave Woods during the last 2 weeks. Anyway, thank you very much.
Questions or comments?
Maybe you know that this concept is already rather well known, for instance, in integrated circles estimation by query in US. It's called twins. So for any point, if you have isotropic random field, for any of these points, if you give a twin, then you will estimate the smoothing effect. Because it's actually just estimating of the correlation function of the smooth Gaussian process. And for Markovian processes, it's also known theoretically.
Okay.
I can give you a paper.
Okay, that'd be very useful. Thank you.
It seems to me that to have like a meaningful test in the end, like here, then you can need a probability function for like a probabilistic distribution over the smoothing parameter. Because right now you have a point estimate,
Yeah.
right? And you simulate from that point estimate, and then see how things change. But that is basically assumes a priori that there is no variability. You already know the smoothing parameter. So learning it, there doesn't seem to be any benefit.
This is the problem of having a sort of semi-Bayesian solution, in that the emulator includes the uncertainty in the regression parameters and the variance. It doesn't include the uncertainty in the smoothing parameter, and that's rather unsatisfactory. We could try fitting them by some general MCMC type scheme to get that uncertainty, rather than use the nice analytical results. And but you're quite right. There is this whole field is dogged by this problem that the smoothing parameters really aren't handled properly. So it would be nice to extend it to do that.
Is it just computational problems that it's just too expensive to handle it properly?
No, we have an analytical solution for half of it, and we don't have an analytical solution for the smoothing parameters. If you try and put them in the Bayesian framework, In principle, you can do it, you just can't solve the equations. So we don't get the nice analytical solution, but I think computationally we could do it.
You mentioned climate modeling. To me, it seems like a very, very difficult task to try to fit some simplified response surface to the result of model simulations if you have such a computational demanding model. In my kind of applications, I typically try to characterize the response surface for models in 10 dimensions, and I still need to run 1 million simulations to get the good characterizations. So if you have such a complicated problem where climate models are notoriously sensitive to input parameters and nonlinear. So is this what people are actually doing, fitting simplified versions or emulators to the response surface of climate models?
Yes, because it's the only way. It's the only way to do it. They're so expensive to run. You cannot run them millions of times. We do diagnostic checks. We do cross-validation. We hold runs back, and it does a reasonable job. The response is relatively smooth as you change these parameters. So as long as the response is smooth, we're probably not doing too badly here. Smooth and not too high dimensional. Once the dimensionality, particularly the outputs, starts to creep up. So we can't emulate all the outputs. We have to pick some outputs we want to look at and the relationship between them rather than looking at the entire temperature field, say. So we have to be a little bit careful. But it does actually seem to work.
So your correlation function has a matrix B in the middle there.
Yes.
Is that order p squared elements then, where p is the dimensionality?
Yeah. In principle, in practice, to make it estimable, we actually make it diagonal.
Okay.
In a sense, if you were doing that in the geostatistical context, that would be a dreadful thing to do. But here we're not trying to reproduce what's happening in reality. We're trying to produce a good interpolating function. So we can take a few liberties, I think, with some of these things and still get away with it.
You're making an isotropic tooth, which means, are you making both elements of this diagonal element, matrix the same?
That's what I've done here.
Yeah,
That one I'm not happy with.
I think that's what is making this ridge of utility happen.
Yeah.
I don't think that would happen if you allow the two elements to be given.
Yeah, but you might get two ridges then.
Yeah.
Two dimensions.
Yeah, I think it will probably pull. I mean, when we did the initial work with Jim, we didn't actually include the prior. We had a fixed value of B, and those ridges were much narrower, and the priors pulled them out, and I suspect going to non-isotropic will pull them out again. I think that's probably right.
Last question?
If I'm not mistaken, what you did here is in a sequential design, you start with a space filling design, adding more points based on some kind of criteria. It's possible to do another more hybrid approach. You start with a space filling design, you try to add in more points based on two kind of criteria. The first one is the utility function you have. Another one is space filling. Let me give you a simple example. You can start with 5 Latin hypercube points. You want to add another 5 points. The two requirements. The first one is you need to maximize some kind of utility function. Another one is the resulting time point still be a Latin hypercube. Was that possible to do?
Do both at once. I don't think we have a utility function. In a sense, you'd like a utility function that includes both purposes, and we don't have that yet. I don't think. The sort of space filling stuff seems to come from a slightly different direction to the utility we're working on here. Well, yes, that's the ideal, would be to combine the two, and then it could decide, yes, I want to do some space filling, I want to do some correlation function estimation, but we're not there yet.
Let's thank Peter again.